Hello, I'm Chris Bauer. I'm the General Chair of ECTC, and it's my honor to welcome you to the 70th ECTC keynote address that will be given by Dr. Doug Yu. Doug is a VP of R&D at TSMC. He's responsible for the development of advanced integrated interconnect and packaging technologies. He has been in charge of on-chip interconnects and wafer-level system integration technology developments. Before joining TSMC, Doug worked at AT&T Bell Laboratories. Before that, he received his PhD in materials engineering from Georgia Institute of Technology. Dr. Yu is an IEEE Fellow in recognition of his leadership in IC interconnect technology development. He was awarded the President Science Prize from Taiwan. Doug has been granted more than 1,000 U.S. patents, and he has over 150 publications. Please join me in welcoming Dr. Yu to give our keynote address. Thank you.
Hi everyone, welcome to the keynote session of the 70th ECTC conference. Thanks to the kind invitation by Dr. Chris Bauer, the General Chair of the conference, and Professor C.P. Wang, I'm very happy to have the opportunity to share our viewpoints on the new path enabled by innovative heterogeneous integration technology for semiconductor industry to go forward. Since I will use the term heterogeneous integration technology many times in the presentation, I will use HIT abbreviation from here on. This is the first ECTC virtual keynote speech. Our colleagues participate from home or office all over the world, which is very special experience. I hope this helps to make this talk less easily forgettable. Technology innovations have driven human societal change for centuries, especially from the 19th century. The pace of technology advances has accelerated over the years, as you can see. From the first digital computer weighted 50 tons to the first suitcase-sized portable computer weighted about 55 pounds, it took 30 years. From the first commercial mobile phone weighted 2 pounds to the first smartphone weighted 18 ounces, it took 10 years. And you can see more examples. New technology innovation accelerated more in recent years. The turning point is in the 50s and the 60s of the 20th century. What makes the turning point so special? That was when the Moore's Law started, which is also just about when our ECTC started. Moore's Law has driven the semiconductor industry for about 70 years. It enabled electronics applications migrate from mainframe computing to personal computing to mobile and to ubiquitous computing, connecting multiple person to one machine, one person to one machine, one person to multiple machines, and nowadays multiple person to multiple machines. As many of you have experienced, these technology migrations caused deep and profound changes of our lives. Nowadays, with the additional capability of AI and 5G, we can expect even more drastic changes in human life. The societal expectations of semiconductor and information technology become both demanding and insatiable. Today we are experimenting with autonomous cars. People expect fully autonomous driving be available tomorrow. But those expectations will not be met without continuous advancement in the underlying semiconductor hardware technologies. Moore's law has lasted for many decades. Over this period, the logic transistor on which we do the computations has scaled down in size by 1,000 times and scaled up in energy efficiency in a continuous manner. Each technology generation enables smaller and smarter electronics with many device technology innovations. However, from 1 decade ago, at 28 nanometer node, many companies, except a handful, decided not to continue technology scaling due to the huge investment needed. In last decade, those leading companies continued the scaling and sustained its performance and power benefits. However, the challenge to continue cost reduction increases quickly with node migration. The cost per function may go up at a point of time in the future if we follow conventional SoC scaling approach. With the innovations on new materials, structure, and design technology co-optimization, we are able to continue SoC scaling for quite a few more generations. However, the challenge on cost effectiveness remains challenged since we are pushing the physical limits of the device. So new innovations are much needed to address device PPAC challenges. While Moore's law faced severe challenge in last decade at the front-end wafer process, something very exciting happened in the back-end packaging area. Here is a replot from yours report. Starting from the announcement Xilinx made in 2011 to adopt first silicon interposer technology CoWoS for high-volume manufacturing. Innovative HIT with TSV has thrived to initiate industry fast growth of HPC. The advanced packaging age began at the year of 2011. Since then, commercial high-performance compact package moved into the third dimension with TSV. Many new innovative HIT applications are launched, such as the HMC from Micron, Light Landing from Intel, integrating HMC, 3D IC DRAM stacking from Samsung Hynix, and more. There are many collaborations among fabless design house, logic and memory IDMs, foundry, and OSAT in HPC marketplace. And in fact, also in 2014-15 timeframe, a new advanced logic CMOS with TSV was introduced in mobile space by a leading smartphone device company. Although this is less popularly known, many hundreds of millions units have been shipped in the leading smartphones. All this market development shows that HIT with TSV has high market potential. Then following, AMD Fiji adopt another type of silicon interposer, CoCos, for GPU HBM1 integration, also for HPC. NVIDIA Pascal gave AI a huge boost from 2016. It is a big new game enabled by several key innovations, including HIT CoWoS. Since the second half of last decade, a new AI wave swept the industry. This is the picture of the first CoWoS package, frontside and backside view. It started from 1x stapler reticle size, which is about 800 mm square, and now it's approaching 3x and even 4x reticle size, which is about 2500 to 4000 mm square, to integrate more and more computing units with higher and higher memory bandwidth and density. From the mid of last decade, industry leaders adopted the silicon interposer to greatly enhance compute power and boosted AI applications. This is achieved again by integrating a larger number of GPU cores and the integration of more memory cubes, and make them closer to the compute engine with significantly less than 100 micron space to enhance the bandwidth and the power efficiency. Also in 2016, a high-performance 3D fan-out package-on-package was first introduced by the leading smartphone company with increased system PPA values. Here's the top view and the cross-sectional view of the new advanced package prior to next level stacking. After the introduction, a slew of TSV-less HIT proposals were made by the industry, including fan-out or a similar embedded die technology. They become very popular in backend area, not only for more smart mobile applications, but also in the HPC area, such as networking. It is attributable to its advantages in compact form factor, potentially more cost-effective, as well as shorter manufacturing cycle time of the TSV-less integration flow. The TSV-less HIT proposals announced here is again a replot from yours report. Now, back to Moore's Law challenges. Cost effectiveness is still challenging with further device scaling, since we are pushing the physical limits. We need new and sustainable solutions to address this issue. The answer to it is the innovative heterogeneous integration technologies. More sophisticated process steps for deeper nanometer device make transistor gate cost reduction more difficult. However, as predicted by both Einstein yield model, that with split or partitioned smaller chips, called chiplets. The yield for smaller chip will increase and the die cost will decrease. More reduction with more splits. The cost-saving effect is more pronounced with larger SoC size as well as for more advanced nodes where the base wafer cost is higher. Other benefits such as cycle time reduction may also be obtained with the chiplet integration. Chiplet integration with HIT silicon interposer has been commercialized a few years ago. Both SoC disintegration and reintegration with HIT may also be challenging in cost, particularly when we have to deal with many customizations. But industry has started to put more efforts to make a general solution to enable higher volume manufacturing to manage the cost. Here is a good example from AMD showing chiplet integration in MCM multi-chip module format. This enables good optimization of system-level PPAC, particularly with cost advantage. A number of chiplet integrations are realized with the new versions of fan-out wafer-level packaging to support applications from mobile to HPC, such as networking. Fan-out wafer-level packaging provides good system PPAC optimization and could further drive system performance and power efficiency. Innovative fan-out wafer-level packaging can enable very broad range of applications. Shown here are examples of a mobile package with size less than 40 mm square, and the other one is actually a full 12-inch wafer for data center, both with longer dies. For mobile, we need to drive to smallest form factor, while integrating about 30 million transistors. For the data center, we need to provide maximum compute power, while heterogeneously integrate about 1.2 trillion transistors. This work is published in this ECTC paper 1.1. Yet another category of chiplet integration examples using HITs with TSV were commercialized in recent years. Shown here is the 2.5D EMIB and 3D Foveros, both from Intel, for chiplet integration. 3D stacking with microbump enables inter-chip communication bandwidth enhancement. Not shown here, other good HIT innovations include HBM in HPC space and the CIS for consumer or mobile. 3D HIT innovation continues. People want to continue push 3D stacking bandwidth density, but it becomes challenging when we want to continue scale the microbump pitch. On the other hand, a new innovative 3D bumpless bonding is a disruptive approach to increase bandwidth density very significantly. In fact, the bandwidth density may increase several orders of magnitude, which would be very desirable. Shown here is SOIC, which stands for System on Integrated Chips. This is an example of bumpless stacking. It can be powerful since it not only reduces the bump pitch, but also reduces the length of inter-chip interconnect. It is flexible for face-to-face, face-to-back, chip-on-wafer, or wafer-on-wafer various stacking. This allows customers to unleash their design and architecture innovations. This technology moves packaging technology from the conventional back-end to front-end stage. All those features have very important implications. Bringing chiplets to closer proximity is very rewarding on system PPA. Vertical bonding density from 2.5D and conventional 3D IC to bumpless 3D IC. Increase the bond density and bond width density. Shorter distance between chips also enables higher speed and higher power efficiency. With the above description and explanation, our vision on the new path forward is based on the three innovative HIT. First is the silicon-based interposer, providing mature technology with stable increased package size for HPC, and fan-out wafer-level packaging for a wide range of application, and SOIC, a bumpless 3D IC in front end. There are lots of mutual leverage among them, as you can see from the simplified flowchart. So our vision on the new path to future, we can do front-end integration using SOIC as an example to enjoy the closest proximity, plus further integration at back-end using either fan-out wafer-level packaging or silicon interposer for critical next stage integration. This 3D plus 3D, or we call it 3D plus super heterogeneous integration, allow us to achieve best system PPAC and cycle time for more than more, for many more years. The flexible integration schemes also help to unleash architecture and design innovations. For the new semiconductor era, we have proposed a 3D ID index, which is defined as the highest horizontal interconnect density times the highest vertical interconnect density between chips or components. And the roadmap for SOP, which is System on Package scaling. This mimic SOC scaling roadmap using a contacted gate pitch as index. This SOP interconnect scaling roadmap targets a 2-4 scaling every 2 years. It can also be accelerated to 1.5 times per year. This roadmap is proposed mainly for industry and academia to align the R&D efforts and schedule to move forward in the Moore's Law 2.0 age. To sustain system scaling, we will do SoC deep partition into chiplets, IP and function deeper and deeper, and then reintegrate with HIT. 3D scaling roadmap need to integrate the chiplets, mini and then micro chiplets with finer and finer inter-chip interconnect pitches. To assess the long-term scalability of the bumpleys stacking, we choose sub-micron bump pitch here to specially match the design rule of a global interconnect via in SoC. As shown here, the bonding yield of sub-micron pitch bonding chain is demonstrated successfully. Here we use a 9-micron bond pitch chain result as benchmark. Preliminary reliability tests results are also encouraging. The tests include both SM stress migration for front-end on-chip interconnect test, and also a typical back-end temperature cycling test. This paper is published in the same conference, so you can obtain more details there. One possible way for us to help semiconductor industry to go forward, in our view, is to provide technology and services on 3 main vectors. First, 3D IC. This is a general term representing advanced packaging and innovative HITs, which integrate and complement to advanced silicon technologies, including continually scaled transistor in more advanced node silicon and special device technologies such as sensor, power IC, RF, mixed signal circuits, etc. All these combine the advancement of software, hardware, co-design. We show here a new and desirable technology trend, which is enabled by innovative HITs. We are going from DTCO, Design Technology Co-optimization, which optimized tools for SoC, to STCO, System Technology Co-optimization, for SOP, a system on package, to best optimize 3 words, IC and system co-design, to enable semiconductor industry to provide many more values to society. Here is a summary on an innovative new system integration foundry. Using innovative front-end 3D HIT integrate with back-end 3D with mutual leverage. We do system integration with chips built on advanced silicon technologies, along with open innovation platform design enablement. We could provide advanced silicon integration foundry service to enable system-level innovations in mobile, HPC, automotive, IoT, and 5G areas. Hopefully, this streamlined system integration foundry can be more effective and efficient. This innovation leverages our IC foundry position and is shared just as an example. In fact, every player in semiconductor industry can have business and or technology innovations and leverage their current establishments to provide better service or product to the industry. New collaboration model will be very important both inside and outside the supply chain. With innovative HITs, packaging engineers now can collaborate more with advanced node front-end engineers to extend Moore's law for more, and also collaborate with specialty technology people to realize better, more than more products and enable higher integration with system scaling and more values. In addition to the collaborations in the device IC area, there will be more opportunity also in back-end assembly and test, system-level engineering, and many tools, including EDA, process technology, and chemical materials. We have discussed the collaboration in bigger scope and broader areas with the innovative HITs. Is that it? Well, not yet. Further out-of-box thinking on collaboration across very different areas or domains could be very desirable for the semiconductor industry to move forward and achieve win-win. Shown here is a new more than more application. Leveraging most advanced technologies in 3 areas. Advanced logic for base or controller wafer. Multi-layers advanced memory. And of course, an innovative 3D plus integration technology. Together, we can deliver a highly scalable, high bandwidth, high power efficiency, high memory density system cubes, better for higher system integration. Here we show that for the first time, advanced 3D stacking with spatial low temperature and low stress 3D die stacking is feasible. Various stack of 4, 8, and 12 layers of memory on a base wafer. Total thickness is easily controlled to be less than 600 micron for up to 12 layers stacking, showing good scalability. The stacking yield and the preliminary reliability results are very encouraging. This is also reported in this ECTC conference in paper 19.1. Are those innovative HITs easy to develop and deliver? Of course not. We need many industry supply chain collaboration and support. For example, we need better transmission mode defect inspection tools, such as CSAM and X-ray. for the inspection of new types defects, such as delamination and cold joint. They both have similar challenge to better optimize resolution and throughput for effective and efficient inspections. There are many more challenges. Thermal solution becomes more challenging every day, especially when we do 3D stacking for more compact systems. Cost reduction versus customization for the higher performance, lower power, more functions. It's hard to achieve economics of scale. This challenge keeps people up all night. Furthermore, we need to continue to grow our company in the years to come. Headaches always. Before we conclude, there's one more point I would like to make. Let's do a little flashback. About just a dozen years ago, which is not that long for 70 years ECT year. That was when logic IC technologies started the adoption of copper low-K and the copper ELK. Packaging engineers has been challenged and all get bogged down by the white pump CPI issue. Relevant back-end and front-end engineers were busy defending and fight for better IC protection against package-induced damages, either by wire bond or free chip. And quite often we heard, "Hey guys, do something please. Don't stop us from shipping our wafers or products." At the same period of time, packaging people were also busy developing eutectic, lead-free, and copper bump. Packaging engineers will never forget this. We were proud to be able to get through it. Today, those protection rules are still very essential and important, particularly for finer pitch free chip bonding. However, some people didn't even notice that we have changed our packaging engineers' long-time roles from defense to offense by those innovative HITs. And the magic power of innovation has literally changed the ballgame. We, the packaging engineers, like a talented basketball player, can make a very good defense play, force a turnover, execute an excellent offense play, and get more fun out of the game. A good HIT innovation not only can provide good protection, but also create tremendous value in offense mode. And by the way, those new HITs, including silicon interposer, RDL interposer, or even bumpless 3D IC, can all virtually eliminate the CPI issues that our fellow packaging engineers have to fight for many, many years. MVP has new definition. The player is a good guard and also score from fast break. It's also a good packaging engineer who can provide exciting values. In this presentation, we share our view and vision on the new path for us to go forward, and have used some examples to encourage our fellow co-workers and inspire new engineers. Everyone in the packaging field can do, and many of them have already done great innovations, leverage their core competence, and achieve higher goals. Making innovations by engineers and scientists is, in many ways, like giving birth to a new baby. There are hopes, excitement, and love in it, and that's the beauty. You create something new, hope to make positive impact, and make the world a better place for everyone. This also makes our job more exciting and enjoyable. Like is said here, the best way to predict the future is to invent it. Together, let's innovate, leverage, and collaborate to invent new semiconductor era. Have fun and good luck. We want to show deep appreciations to TSMC colleagues in various groups and supply chain collaborators for their outstanding contribution and support to this work.